This is Rohit Patel. I work with Emphasis. I have my colleague Ashutosh Vyas with me. Today we are going to take a quantum machine learning webinar. Thanks for the government of Telangana for inviting us to this. So this is the agenda for today. We will start with an introduction to quantum computing, a short review. As I understand, the students and the participants are going over quantum computing since 4th of April. Our session will be focused towards quantum machine learning, but it's better to start with a short review of quantum computing so that we can set the context. Then we'll move on to some applications of quantum computing. From there on, we will move to the main topic of discussion, quantum machine learning, where we will look at, we will have a more focused approach on the practical aspects of it. We'll try to broadly cover the overall area rather than going into specific algorithms today, given this is the first webinar on quantum machine learning. So we'll look at QML on gate-based, annealing-based, and quantum-inspired systems. Jumping on from there, this will more be an exercise on how you can create workflows, how you can use algorithms to do quantum machine learning on these systems. We'll move on to doing QML on Qiskit. So if you have been going through quantum computing, you must have seen that companies like IBM, Google, Rigetti, IonQ, and others have been releasing their own platforms. And today we will focus on Qiskit, where we will show you the platform they have. We will give you a platform walkthrough. We'll show you a simple quantum circuit, and then we'll move on to a QML use case. After that, we will walk you through some quantum knowledge resources that have been helpful to us within our journey for over the last 2.5 years. At the end, we will show a very brief of what we are doing at Emphasis in the area of quantum computing, and we will take questions and answers. Now, just to repeat the quantum team with you today, I am Rohit. I lead the quantum computing practice at Emphasis. I am the Associate Vice President here. I have my colleague Ashutosh here, who's a Senior Manager, Data Science and Quantum Computing. He's co-leading the practice with me. And today we'll be taking this session. So this is the first section we will go ahead with. As I understand, you can post your questions in chat and we'll try to answer those during our session. Whatever questions are left, we will take that at the last. So this is a brief overview of how digital computing has evolved and the systems have become smaller. So we can look at computing from further back. For example, we can look at the mechanical computers developed by Charles Babbage, the difference in analytical engine, which were mechanical in nature. But they were very big. They could solve very few problems that were of practical importance.
Sir,
with the advent of...
Sorry to interrupt. Can you have a full screen mode for the presentation, sir?
It is already full screen from my side.
All right, sir. Thanks, sir. Thank you.
Okay. So from the digital computing standpoint, we can start. We started from vacuum tubes. We moved on to transistors. Then we moved on to integrated circuit. Then we moved on to microprocessors. And now, so this is one of the ways we have moved from electronic computing standpoint. If you do a little more research, what you'll find is that there are many alternative computing technologies, though not all are physically or practically feasible at this point in time. You can use chemistry, for example, to do computation. You can use DNA to do computation. There are multiple systems in nature that allow you to do computation. One of those systems which have become practical other than the classical digital computers, classical digital electronic, I should say, is quantum computing. So we'll talk about why quantum computing, what and why of quantum computing. Okay. So the idea is, first of all, let's talk a bit about what is computing. So we are talking about a programmable computer It is a machine that can carry out sequences of arithmetic or logical operations automatically. How it helps us is it allows us to solve real world problems. You can think about problems from industry standpoint, problem from physics, chemistry, and I'll show you some of those applications. A programmable computer is a machine that can solve these problems by using very basic units of computation. So before I jump to what is quantum and why quantum, we need to know how computers can be differentiated from each other. So you can look at different levels. You can look at the physical substrate of computation. You can look at the model of computation. You can look at the architecture, how the computing elements are arranged. For example, the current classical computers that we use today on a daily basis are based on the model of classical physics, where you use transistors as switches. It sits on top of an architecture called von Neumann architecture mostly, and then it uses classical algorithms to solve problems. To understand why quantum computing is better possibly, you have to go into the concepts of the theory of computation. So what quantum computing has done, it has brought back focus of masses to back to the idea of computation. If you look at the field today, the idea is mostly shifted to how we can use libraries to build applications to solve real world problems. So basically, we have built several abstraction levels to identify problem solving skills. But in this particular case, we have gone back to the idea of what a computation means, and that can be studied under theory of computation, that deals with what problems can be solved on a particular model of computation using a particular algorithm and how efficiently you can solve it. You can solve a simple problem like searching something in a database in 100 years. You can do that also in a millisecond. So different model of computation, different algorithms bring those things out. So what is quantum computing? Quantum computers basically harness the unique behavior of quantum physics, such as superposition, entanglement, quantum interference, parallelism, and tunneling, and apply it to computing. But how does that help us? The idea is quantum computers have disproven Church-Turing thesis, in turn developing algorithms. So what is this Church-Turing thesis? This particular thesis says that if you look at the classical domain of computers, the problems that we are solving today, the algorithms that we have built on classical computers, there are no alternative models that have been found which can solve problems any faster. Two models that came into picture which tried to disprove this thesis was the analog computers and the probabilistic models. But for many practical applications that we see today, both of these models can't be better than our classical computers. But quantum computers have given us algorithms which, when implemented on a quantum error corrected larger quantum system, will solve certain problems very fast. Now, given quantum computers can solve certain class of problems very fast, we can solve complex industry and academia problems efficiently using quantum algorithms. So things like synthesis of new materials, drug discovery, climate forecasting, these fall in the area of high performance computing. You require supercomputers to do these things, and the current supercomputers cannot handle a big problem at this stage also. So if you look at proteins, if you look at such molecules, some of these compounds are thousands of molecules long, right? And even if you try to simulate, let's say, water, which is a very simple compound, it is not that easy to do it in a classical computer. Forget about the larger compounds. So the idea is quantum computers can provide that advantage. Then the idea is, if you look at the classical computers, if classical computers had to provide that computational advantage, that could have allowed you to basically improve the processing speeds and execute these use cases faster. The miniaturization that allows classical computer to do this, the packing of transistors on a chip, right? That is being affected by quantum effects today. Generally, when you talk about classical computers, we are looking at whether we can detect a 0 or a 1 correctly or not. Those things can be impacted by quantum tunneling effects and such things as device size decreases. So classical computers, you cannot make them more complex now unless you deal with those effects. So the alternative model of computing that we have is the quantum computing model. And the final thing is natural systems are quantum mechanical in nature, and simulating those requires if they can be better done on classical computers than on quantum computers than classical computers. So we will talk about. So if you look at any computing model, the idea is you have some information or data to begin with, and then you transform it over time. Now, the information representation generally has to be done in electronic form if it's an electronic computer, right? So if you look at classical computers, they store data information in form of bits that represent 0 and 1. Now, if you have, let's say, a 3-bit system, at one time, those 3 bits can represent a single state. And these are the states you transform over time. So if I ask you to add 2 numbers, 2 3-bit numbers, you'll take first number in a 3-bit form, let's say 7, and second number in a 3-bit form, let's say 5. So you are trying to add those. And to do that, you're basically transforming the state of these 2 numbers to a final addition that you want. In comparison, qubits can exist in superposition. They can have a 0 and a 1, but they can also exist in superposition of these states. This we will explain in context of quantum machine learning going forward. And I'm assuming since you have had some idea about quantum computing, I won't explore it at this time. Next idea that we have to look at is the entanglement side of things. Now, how does an entanglement impact quantum computing is more important than what is entanglement in general. The idea is certain entangled states allow you to do computing better because impacting a particular qubit, applying a transformation on a particular qubit, impacts calculation of others also. That is one important thing we'll look at going forward. Now, you have the input information in form of qubits, let's say, but you want to execute it somewhere, right? So generally, we talk about the information processors in quantum case, and these come out of model of computation and the practical quantum computers that are feasible out of it. So a model of computation generally describes how a mathematical function is computed given an input. The same, you are looking at one model of computation in classical systems today. You generally work on your PCs, servers and all. They follow the gate model of computation. That is the underlying physical layer is put in form of gates. There are other models also in place, for example, random access machine and others, which can be used, but primarily the computers today are based on gate model of computation. Similarly, in quantum side also, there are multiple ways you can build a computer. Here again, the quantum circuits, the gate-based systems are the ones which have taken precedence. There are multiple reasons to it, but we won't go into that. But these computers, their prototypes with decent number of qubits have also come out, which you can use today. For example, IBM, Google, Rigetti, IonQ, all these have their computers available over cloud, over general clouds like Azure, AWS, and GCP, and they're also available. Over their private clouds. Now, these have become feasible. You can use them, but there are other models you may not. For example, one-way quantum computer is proposed as a mathematical model, but people are still trying to create a physical computer out of it. Adiabatic quantum computing based on quantum annealing phenomena, of which D-wave is the main example, right? It allows you to do computing in a different way than the quantum circuits. Quantum circuits use gates to do the computation. We'll explain what gates are. Adiabatic quantum computing looks at an input problem, and it evolves it over time, let's say. So you get a solution. So computing can be done in various ways. We are showing some of the ways here. There's something called a topological quantum computer. Microsoft is building the same, and once it comes out, it has certain advantages that could be realized. Finally, is a quantum Turing machine. This is not a practical quantum computer. This is a quantum version of a theoretical probabilistic Turing machine. And generally, when you talk about looking at algorithms, how good they are in comparison to classical computing, in comparison to, let's say, probabilistic computing or deterministic computing, you try to compare the results against quantum Turing machine. Now, you have the information, you know where to process it, but when it comes to applications, you have to build something. And the first step in doing that is using quantum algorithms. So quantum algorithms is nothing but it is an algorithm which runs on a realistic model of quantum computation, that is a physical quantum computer. You know an algorithm, what does it mean? It is a step-by-step procedure where each of the steps can be performed on a quantum computer. So we have divided the algorithms into three parts: pure quantum, hybrid, and quantum inspired. If you look at it, it is moving from quantum to classical. The first one runs, the first one mostly will run on a quantum computer. The hybrid one uses both quantum and classical computers. And the quantum inspired version, these are generally classical systems which have taken certain properties out of quantum computers and build algorithm or systems which can solve problems better. So these are the three layers. Pure quantum generally makes use of certain components which are not available today, like quantum RAMs and all. You can replace those. You can do real-time encoding of data, for example, but it will not deliver the benefits, the exponential speedups that you would expect otherwise if these algorithms were run on a quantum RAM plus an error-corrected large quantum computer. So we'll explain these a bit more later, but the idea is that quantum algorithms can be divided in this particular way. There are some algorithms we have mentioned here. For example, you must have heard of Shor's factoring algorithm, Grover's search algorithm, algorithm for solving linear system of equations, the HHL, the Harrow-Hasidim-Lloyd algorithm, which basically allows you to do machine learning, for example, in cases of regression. Then you have QPCA, QSVM, QClustering, that all have been mathematically shown proven speedups, but only when you use a Qram in place. From annealing side, you can see quantum annealing for sampling and optimization, and there are some quantum simulation algorithms. Hybrid systems move a bit away from this structure, given Qram and error-corrected systems are not available. And they are trying to get the computational advantage promised by quantum computers by a method which is making use of parameterized quantum circuits and using a classical optimizer to solve the same. Quantum inspired both come in form of hardware and software. A very interesting example is after quantum annealers, something called digital annealers came into place. So earlier I said that computers can be differentiated in different ways. So this quantum annealer and digital annealer are differentiated from normal gate-based computer at architecture level. They are different architecturally. They do not have a central processing unit. They do not have a separate memory. It's a distributed computing kind of setup. So looking at these quantum annealers, digital annealers, which completely use your normal switches, CMOS-based switches, for doing optimization or machine learning or for other purposes. Next is, okay, now you have the information, you know where to process them, you need the algorithms, but to build those algorithms, you need programming languages, right? That you see every day. We have moved starting from assembly languages in classical domain to high-level languages. So in the process, you build compilers, you build interpreters, you build all those things. Right, so this is a picture. So we have collected a lot of resources from different places. This PPT is made in that particular manner. So you can look at different levels of programming languages that are available to us. So at the end sits the hardware. On top of it, very similar to how classical computers work, you have assembly languages. So you can look at OpenQASM in IBM. For Rigetti case, you can look at Quill. D-Wave, you look at QMASM. Xanadu, you can look at Blackbird. Google, you can look at Google, Microsoft. Kilimanjaro, you can look at other quantum machine language instruction languages, right? Similarly, to build quantum circuits, general quantum circuits, you can look at Qiskit-Terra, PyQuil, QBSolve, so on and so forth. Similarly, for building quantum algorithms at a higher level, you can look at something. And there are end-to-end libraries. So mostly you use end-to-end libraries, full stack libraries to build algorithms for different applications. So you can have a look at these. I'm not going into this given the time we have. Now, you have all the components that you require to process the information, right? The information representation, the quantum computer, the algorithms, the languages in which you can code the algorithms. The last part is how do you put this into perspective? So these are two pictures which will basically puts that into perspective. You start with a quantum algorithm, you code it, and then you have a runtime very similar to what you have, for example, in classical system. You can have a compiler, you can have an interpreter, those kind of things. Now at the bottom layer sits the hardware. And this hardware, as I said, can be of different type. So each type will encode the problem differently. So if it is a very gate-based system, very similar to our classical computers today, each of those CPUs will have an instruction set in place, right? So given a basic set of instruction, can you convert a higher level quantum algorithms to those basic steps to process on a quantum computer? These are the different layers that are there. So quantum error correction layer 3 on the left-hand side is one important case that we have to look at. Currently, digital computers today work at scale. Basically, they can solve very large problems because of the error correction algorithms that they have in place. Otherwise, both communication as well as computing would not have been possible at the scale it is today. Quantum error correction is a field which is currently being looked at. Once that comes into fore, you can have a fault tolerant / quantum error corrected systems. Okay, so before saying a few points to consider, like before we adopt quantum computing, like why another type of computer we have already discussed, the benefits it delivers. But it cannot be applied in all the cases. For example, if you want to go and do web browsing or play very simple games, quantum computing is not the right answer because classical computers can do it as well, right? So there are certain things that you have to look at, some of the areas that you have to look at. If you look at optimization, machine learning, communication, simulation, cryptography, these areas can benefit from quantum computers. It is look at it as from a coprocessor standpoint. You had CPU and it used to process graphics. Now you have a GPU. GPU becomes a coprocessor to CPU and handles all the graphic related tasks. Similarly, quantum processor becomes a coprocessor which handles certain routines passed on from the classical computer. It provides you a disruptive advantage, but only in certain scenarios. For example, optimization is a big use case. You can look at problems like route optimization, portfolio optimization, manpower assignment, crew assignment, such kind of things. But not every problem will deliver you the benefits, and research is still going on what exact problems can it provide benefits on. So I'll move on to application of quantum computing. So this is a broad level picture again on where can you apply quantum computing. So you are looking at the areas of mostly sciences, because sciences will definitely benefit from quantum chemistry, quantum biology, using mathematics to solve problem in encryption, quantum internet, these kind of things. Now, biology and chemistry together can deliver the benefits of better drug development, development of biomolecules, better material development, right? These kind of things can be done. Like these are the application areas, but if you look at the computing side of things, how these things will be realized, it can, quantum computing can allow you to build better algorithms. In fact, even if you can't build a better quantum algorithm today, it's a hard job to do. Classical computing is getting the benefits due to the research being done in quantum computing. So I will move on the industry side of things, because just talking theoretically about the concepts in quantum computing may not help you. So we look at certain areas like supply chain, logistics, retail, and manufacturing, and you can see a lot of use cases that you can solve. And many of them are in area of optimization or machine learning, and sometimes simulation. So Volkswagen already has tested this out. Many companies are doing it, JPMC, Volkswagen, and all these. And they're looking at traffic optimization. And it has already deployed QC for fleet management to optimize taxi routes in Beijing. Coca-Cola bottleless Japan is exploring how quantum can better optimize its delivery. And there are 700,000 vending machines, a big problem to solve, most probably being done by in-house systems, because the classical algorithms for optimization that exist today, the runtime will be too high for a business to use it efficiently. You can look at in-store logistics, you can look at inventory sourcing, you can look distribution, and these are industry examples. But on the left-hand side, you can see in general problems in supply chain that you can solve. Route optimization, aggregate risks such as supply chain interruption, simultaneous packing of parcels, traffic optimization, last mile delivery, scheduling, and demand prediction can be done. Financial services is one of the areas which is being primarily targeted by quantum computing. So again, the problems can range from portfolio management, which basically allows you to build a portfolio given a set of securities such as stock, bonds, and other things. This allows you to, this area basically allows you to invest and reap benefits. So how much money to put in stock A versus stock B versus stock C, that becomes an optimization problem, and quantum computers can get you better answers in our experience. You can do risk profiling and credit screening. You can look at market simulation to optimize investment and hedging strategies. You can look at QML to build macroeconomic forecasts. Now you have right hand side, you again look at different companies and what they are doing. JP Morgan is looking at improving their trading strategy, how to price options and predict the price of financial options. You can look at security pricing. You can look at optimizing loan portfolios. These companies hold multiple loans, right? Given the size of their portfolio, they may want to see which to keep and which to discard, for example, right? So diversification is one very important area you can target. I think somebody has posted a question in chat. Ashley, if you want to look at it and answer, please. Yeah. I will move on to the automotive side of things. Automotive insurance, I'm not sure why it is not going away. Okay, so I'll continue. From automotive insurance pharma perspective, you can look at material science and simulation. So you can think about new materials, better materials. For example, how cars are made today. We are reaching very light materials. Aluminum has been used to make aircrafts and all. Can we create better materials to create lightweight, stronger aircrafts or cars and everything, right? You can look at drugs. Certain diseases currently do not have any drugs that can effectively treat them. From that standpoint, a lot of drug discovery research is done, and mostly it is being done in an experimental manner. But if you can bring computation in perspective, you can bring computational chemistry, computational biology to through quantum computation, a lot of simulations can be run, and possibly better drugs can be developed. So there are many more use cases. You can look at NLP also. So when you're looking at any of the industries, Look at different type of data they have. So data starts from the structured data. It goes on to unstructured like images, the data in form of text, the data in form of videos, all that can be done. Anomaly detection, for example, becomes a very good use case where you can use different data sources to solve a problem. Now, you will hear a lot of new names coming in when you're talking about quantum computing. So there are device providers, plant equipment providers, quantum computing manufacturers, cloud service providers, and software providers. We have put some of those here, like who are the full stack providers, starting with Google, IBM, Microsoft, and others. Then you look at software applications, who's building those, right? So Riverlane, QCware, Zapata. Then you look at cloud computing, who's available on cloud also. So OneQubit is one of the companies. You look at quantum encryption in AI, systems and firmware, and then the quantum hardware providers. Okay, so I think I will hand it over to my colleague Ashutosh. So we will switch between the two of us and we'll go through this. Ashu?
Yeah. So, hi everyone. So till now, we have understood a lot of things about quantum machine learning, how quantum computers have evolved over time, and what all quantum machine learning can achieve going forward. So now let's have a deep dive into the concepts of quantum machine learning. The first question occurs in mind is like, what is quantum machine learning? So quantum machine learning is something or a research area where people use quantum computing methods or quantum computing ideas to perform machine learning tasks, as simple as that. And why quantum computers? Rohit has answered and given a lot of points. But as you know, there is a requirement which is keep on increasing for machine learning tasks where data is getting bigger and bigger day by day. And you require something more powerful now to churn all the patterns or to churn your data and to extract relevant information out of it to get your goals done. So this exercise requires something more computationally strong. And what is better than quantum computers, right? So that is the basic reason why we are moving from classical machine learning to quantum machine learning. Rohit, can you go to the next slide? Thanks. Now, what is the point of interaction between quantum computing and machine learning? How do these two systems evolve and interact with each other? Let us try to understand this in three different parts. So there is a machine learning model which you would like to train. Quantum computing will help you do that. There are a lot of features in your data set in classical domain, and you want to recognize or understand different patterns involved in those features. Quantum computing will help. And if there is a sampling problem, you have a probabilistic a probability distribution which is way too complex, and even Monte Carlo Markov chain sampling strategies are taking exponentially expensive time and compute to solve them. Quantum computing can help in that case also. So fundamentally speaking, there are three different domains: training, pattern exploration, and PDF sampling that actually helps machine learning to train your models better, to explore your data sets more deeper and deeper, and suppose in a generative model scenarios, do a better sampling with less correlations and fast, and do this exercise fast too. Now let us take all of them one by one with a small note, and we will discuss all these going forward also. So how it helps in training? So it helps in training basically by, suppose you have a machine learning model and you want to, the most expensive part of any machine learning problem which requires a lot of compute is doing the optimization. So suppose you have a neural network and you want to optimize the network. How would quantum computing can help? You can take use of quantum computers to perform that optimization task. That will be faster enough. That will generate better optimal points for you, and your training will eventually be faster in that case, correct? How do pattern exploration is catered using quantum computing? So there are fundamental concepts involved in quantum mechanics, something called as entanglement. We will see in our next coming slides. Entanglement is a property of quantum mechanics which actually helps you to generate correlations between your feature information. So some information may be non-linear and you do not, or you are not able to capture in your classical machine learning model. You go ahead with a quantum computer gate-based systems, and those features which you feed into your quantum systems will capture those hidden patterns and informations. This might or might not help in the machine learning objective. That's another scenario, but you will definitely be generating more correlation between the variables. So resulting into a better exploration. How PDF sampling or probability distribution function sampling is catered by quantum machine learning. There are certain quantum computers which are annular based, as Rohit already explained. These systems generally perform in sync or as similar as Monte Carlo Markov chain sampling. So there is a functionality with which you can actually pass your PDF function to a quantum annular, and it will do the job for you. It will reduce the time of generating samples. It will generate less correlated samples for you. So the estimated point which you will get, or the point estimation of the PDF function which you require for your machine learning objective will be better. We will also see a use case going ahead using and Boltzmann distribution. Rohit can move to next slide. Yeah. Now, with all this said, how do you know that you actually are going to get something from quantum machine learning? Let's have a look about that also. So the first point which we propose is compact information representation. As Rohit already stated that in classical system, you have bits or your ICs work on bits. Bits can handle only one information at a time. But in quantum systems or in quantum mechanics, you have qubits. Qubits actually are represented in a superposition of multiple states. To put it in a very, very simple example, suppose you have an electron. Electron can have clockwise as well as anti-clockwise spin at the same time. Because of Heisenberg uncertainty principle, you cannot know the exact momentum and position of that electron. But there is a probability with which the electron can exist in a clock spin and anti-clock spin. So if suppose my qubit is an electron, then what I will do is I will represent that electron into a superposition state of both the spins, considering zeroth cat vector as a maybe anti-clock spin, then the one cat vector representation as a clock spin. When you do this exercise, when you represent your information in superposition, then what actually you achieve is parallel computation. You can explore the dimensionality of your mathematical computations using clock spins also. In the same time, you can do the same thing and the same exercise with your anti-clock expression of information also. So this kind of combination or this superposition capability enables your system to do a lot of mathematical computations parallelly on the same device. This is the first advantage. Second is the efficiency of the feature space exploration. As I already mentioned, because of entanglement. Entanglement, now let's have a slightly more look into what is entanglement. Entanglement is something when you take two quantum particles and bring them together in some kind of an interaction. And because of that interaction, now these two particles always exist together. Suppose, now how it helps with your machine learning task. So when you have, suppose you have a feature, or suppose your data set have only two features, and you did on every feature you have used some kind of embedding and you've passed that information to your quantum system, and now you entangled them. When you entangle them, what the quantum mechanics or quantum computing will do at the back end is, it will start generating correlations between these two systems together. And because of these two features getting correlated with each other, you will start getting a lot of other quantum states, which will be entangled states, of course, but those states, the new states which evolve, will represent some kind of a correlation between these two features. Now, this actually helps in, again, I would say it may or may not help in your machine learning objective, but definitely you are getting more orthogonal vectors for a representation of your classical data set into quantum system, which actually explores and exploits the hidden patterns in it. Now, the third point is faster training and optimization. So, as we already discussed, that optimization is a very expensive task. It requires a lot of time as well as compute. Now, as your parameters will grow in your neural network, suppose, or your deep neural networks, when you are using autoencoders, when you are using RBM, restricted Boltzmann machine, as the number of parameters will grow, the compute time and the compute itself will be expensive. And to resolve this issue, what quantum computing can help is it can provide you faster optimization with the better solutions. How it do it is something we will discuss in the coming slides, which will be called as quantum annealing, as Rohit already mentioned before. So these are the fundamentally three areas why we want to use quantum machine learning going forward. Which can we move to the next slide? Yeah. Now, based upon our understanding, let's divide this quantum machine learning system into certain three kind of a structure. So the first part of quantum machine learning can be called as quantum computers. And second part can be called as classical computers, which are leveraging quantum mechanics or quantum theories of physics to design algorithms in classical, staying in the classical domain itself. So quantum computers can be gate-based systems and they can be annealer-based systems. We will look going forward what is gate-based system. We will also see how annealer-based systems work. But for now, you can consider gate-based system as kind of a circuitry, as it happens in your ICs. An annealer-based system is a kind of annealing process happening in a quantum physics or quantum mechanics space, where certain things evolve with temperature and time. These two fundamental concepts purely can exist in a quantum computer. Now, on the other side, when we say that we have classical computers also, what do we mean by quantum-inspired systems? So quantum-inspired systems are systems which solely perform their operation, first of all, in classical domain. They will never go or move the data to classic quantum computers. But what they will do is they will adopt the theory of quantum physics and quantum mechanics into their classical computation environment and do the further processing or perform their algorithms of machine learning. Now, this can happen in both the ways. You can actually mimic quantum gates also. You can actually mimic quantum annealing also in the space of being still in the space of classical computation domain. Moving forward, we will see what all kind of algorithms we can develop and design using all these kind of systems, gate-based systems, annealer-based systems, as well as quantum-inspired systems. Rohit, can we move to the next slide? Yeah. Okay. So let's start our journey with quantum gate-based systems first. Before even starting this journey, the fundamental concept we need to understand to know the mathematics of or to design your own mathematical functions, something called as bracket notations. It is another representation of vectors. You have already been seeing from your 12th grade or 10th grade itself how vectors are represented. So vectors basically are something which expresses a position, a dimensionality space. If a vector is present in a real real space, maybe a 3-dimensional or 4-dimensional space, that all theory comes under a part of a classical vector representation. But what happens in quantum? In quantum, we actually have our operations or vectors exist in a Hilbert space. Hilbert space is something which has infinite dimensions. So you need a certain different kind of notation to represent your vectors. That is called as ket notation. Now, if you will see on the screen, a ket notation is expressing a quantum vector in a Hilbert space. The notation can, a ket vector can always act as similar as a classical vector. You can add or multiply numerical numbers to these vectors. You can add 2 vectors also. But the critical idea or the important idea behind is that every ket vector has to be or can be represented by a combination of orthogonal bases. These orthogonal basis vectors actually um, uh, are the vectors which are representing that space or the in which the superposition has been expressed. So moving forward, we will also see that a qubit which we are using, how that qubit will be mathematically expressed as a linear combination of different basis vectors. Now, what is bra notation then? It is nothing but a Hermitian conjugate of your cat vector. You have to take your cat vector, do a conjugate and transpose it, and you will get a bra notation of it. Now, so you can also see we have given a small example on the screen. Suppose a cat vector looks like, suppose we have two basis vector A and basis vector B, both have their cat notations and both are orthogonal with each other. And the notation looks like 4 cat vector A plus 6 iota cat vector B. Now, if you want to represent this expression in your bra notation, it will be, you will have to reverse the vectors A, orthogonal vectors A and B into bra notation, as well as the iota sign will change. This is how actually we represent our bracket notation. This is a fundamentally important concept to understand, to know the mathematical expressions, and it makes it easy to perform operations if you know bracket notations. Wait, I can move to the next one. Yeah. Now, let's again have a look how quantum states are represented. So quantum states are nothing but, suppose you have input information and you want to express that information into a quantum mechanical space. That information can be expressed using quantum states phenomena. Going forward, we will see certain kind of embedding strategies where you can bring your classical data into a quantum space and you can express your classical data into quantum state forms. Then the second concept comes as quantum algorithms. What are quantum algorithms? Quantum algorithms are basically using these quantum states, so these quantum states are prepared from classical data, and quantum algorithms are using these quantum states to perform certain kind of computations to achieve a certain goal which you want. Suppose you want to develop a classification problem. Quantum algorithms will leverage these quantum states or perform certain actions or computations on top of it to learn something in quantum space itself to perform that classification task. Similarly, we can do it for optimization, regression, maybe simulation modeling, whatever comes under AI paradigm. You can perform all that operations using quantum algorithms. There are just a few representations which we have put on the slide, just to have a feel how certain things can be expressed. So a single qubit can be expressed in two classical orthogonal states, cat notation 0 and 1. Suppose you have a qubit, and we already know that the qubits right now can be existing in superposition of two states. This is how the expression looks like. Again, a qubit superposition state to a multiple qubit system. Suppose you have two qubit systems. When you have two qubit systems and you want to express both the systems together, actually what fundamentally you are doing is you are expressing, or you are entangling these two qubits and then expressing the final quantum state in terms of a cat notation. When you entangle them, the expression of a superposition will occur in 4 different orthonormal basis vectors. That is what qubit system second example represents here. So if both the qubits are entangled, now you will have 4 positions, because every qubit can take 2 states, 0 and 1. So the combination of 2 qubits will become 0, 0, 0, 1, 1, 0, and 1, 1. This is how your orthogonal basis will look like. And then you can express your qubit state, joint or entangled 2 qubit state in a superposition form. That is how the second example expression looks like. Now, there is let me give you a brief here itself. You see there is something written as where the modulus of all the magnitudes is equal to 1. This is nothing but a probability amplitude. We will discuss more about this in our next slide. But we can go to the next slide. Yeah. Now, till now, what we have understood is we have seen what quantum machine learning can do, why it is used. We have seen quantum state expression using cat notations and what is its Hermitian transpose. Now we want to understand what are the basic fundamental principles on which these quantum states are expressed. There are three fundamental principles: superposition, entanglement, and interference. These three fundamental principles help you represent your information into form of quantum states. Let us look all of them one by one, starting from superposition. So superposition is a linear expression of your quantum state in terms of orthogonal bases. I am reiterating the same thing, but the important part here is once you express your quantum state in terms of a superposition, you always have to understand that the magnitude associated with each and every orthogonal basis vector is a probability amplitude, which means that once you collect all the probability amplitudes from your quantum state, square them and add them, it has to be equal to 1. Why this theory is important, why this concept of adding in all of them and putting them and summing them should equal to 1 is important, is because you fundamentally what you are saying about a superposition of a quantum state is that your quantum particle can exist in any of the quantum orthogonal basis with a probability. And that probability is expressed in terms of probability amplitude in your expression of superposition. That is the reason all of them should, their modulus square should always sum to 1. This is the fundamental first principle, which we call as superposition. The second principle, which is very, very important, is entanglement. Now, entanglement is a phenomena which I think some questions are coming. Okay. Entanglement is a very, very important concept in quantum mechanics. What the reason because is what it does is it is bringing your different qubits together in a certain manner that going forward, once they are entangled, they will never exist separately. You cannot measure one qubit separately once you have entangled your system. And even the distance do not matter once the entanglement has happened. Suppose two particles have entangled. Now, whatever may be the distance between them, they will behave in a certain fashion. That is the main principle, which is amazing. And actually, it has blown the researchers' mind when they have seen it happening. Now, let's discuss how mathematically you can do this exercise. Suppose you have two vectors, vector A, which is also which is a quantum state, and vector B, again, which is another quantum state. Both of them are existing in superposition of 0 cat and 1 cat. Their matrix representation is also, you can see on the screen. Now, let's do a mathematical entanglement on top of them. Once you entangle quantum state A with quantum state B, the final expression which you will get is a new superposition, which is having 4 different orthonormal spaces or orthogonal basis vectors with an amplitude of their multiplicative amplitude of vector A and vector B. So what are these new orthonormal basis vectors? They are nothing but 0, 0, 0, 1, 1, 0, and 1, 1. So it will follow a factor of 2, an exponential factor of 2. It will follow, like if you have 2 qubits, you entangle them, you will get 2 raised to the power 2 states. That many number of orthogonal spaces. Now you have 3 qubits, you entangle all of them, you will get 2 raised to the power 3 states. And we will see this happening physically also when we'll show the demo. The third principle, another very important principle, is interference. Now, we all know that quantum particles express their existence in wave form as well as matter form. When we go ahead and study the wave formulations of quantum physics, their wave expressions, now waves do interfere with each other. Those interferences can be constructive or destructive. From that concept, we are bringing a phenomena for quantum computing called as interference. We can actually leverage this mathematical expression or this physical phenomena to develop or understand the parameters of your data set using interference. A simple example which we have posted or which we have added here is like, suppose you have a psi vector. Now the psi vector is again expressed in 0 notation and 1 notation, and you perform a Hadamard gate to a Hadamard operation on this psi vector. What will you achieve at the end is the component of one cat vector will cancel out each other. Physically, if you will express this thing in a quantum computer, and you will look from an angle of wave expressions of quantum physics for that quantum particle, it eventually is doing destructive interference with each other for cat1 and doing a constructive interference for the zero cat vector. So finally, what you are achieving is a zero cat vector. Now you can always design your quantum systems using wave mechanics because quantum particles do express their existence in terms of wave theory of waves also. And also you can do the similar kind of in their matter form also. You can, so researchers have leveraged both the methodologies to design their quantum machine learning algorithms. Yeah. Now, so what we have understood till now is we have seen certain principles, we have seen notations of quantum states, how they can be expressed. So how about going ahead and designing a machine learning model out of it, which we will call as quantum machine learning using a gate-based system. So this particular slide expresses a journey required from starting your data in hand, which is in a classical domain, any data set which you see in your pandas libraries or in your CSV file, taking that information into to a quantum computer, solving or training that model, leveraging quantum computing to do that, and getting a final result out of it. I will just walk you through this system from left to right. The first step of doing is state embedding. You require certain methodology of expressing your classical information into a quantum state. You will have to bring your classical data to a quantum computer, and there is a certain kind of embedding which is required. Once you have done that, once you have brought your data into a quantum system, you are actually expressing your data into a superposition of different qubits. Number of qubits which you are using solely depends on your problem, how you are doing your embedding, and the feasibility or availability of those number of qubits for a system. Okay. The second, next is once you have designed your superposition, the next part comes as your entanglement. Now you do start developing certain kind of circuitry, mathematical computations on your this quantum state to learn something or some patterns out of it. When you do this, there will be a lot of interference happening. There will be a lot of destructive and constructive interferences happening. And the objective of that entire circuitry is to bring you to a certain point where you actually achieve your goal. You do a better classification, you better regression model. Once your circuit is trained, you need to measure the output from the quantum system because we know our systems better in classical. So the next we will do is we will do a measurement on your quantum systems. That will be the final part of bringing your data to a classical system and taking it out after using a measurement. So that's the entire journey. We'll go through this journey in our coming slides. Yeah. So as we already stated, the fundamental first step required is to bring your classical data into a quantum system. That is called a state embedding. There are fundamentally three kinds of state embeddings which can happen: basis embedding, amplitude embedding, and length embedding. Let's quickly go to all of them one by one. What is a basis embedding? Basis embedding is very, very simple and a fundamental one. You need to represent your data set in a form of zeros and ones. You will have to use binary encoding on your classical data so that it can be binary hot encoding, it can be different types of binary encodings are feasible. So you can use any of them using your pandas library. Once your data is expressed in terms of a binary encoded form, you can just you know that each and every feature of your data set can be represented and can take only two values, either 0 or 1. So the number of qubits required in this kind of a scenario is exactly equal to the number of features you have, because each qubit can exist in both the states. It can be in 0 and 1. And your data set also has that many number of features where each and every feature can exist in only two states, that is 0 and 1. Suppose, so there is a small example which we have put. So So example says that suppose you have a point x1, which is 0 and 1, and another point is 1, 1. Only 2 points are there. So the entire data set can be represented using two qubits itself, and using those two qubits, how your data would look like is represented in the expression below. Let's quickly jump to the amplitude embedding part. Amplitude embedding is something which is using probability amplitudes, which we discussed before, to represent the classical information into a quantum state. How they do it is like, suppose you have an n-dimensional data set. Now that n-dimensional data set needs to be represented in a quantum state. So what you will do is you will just do a small mathematical computation, that is capital N equals to 2 raised to the power small n. This small n will actually represent the number of qubits required. Suppose you have 8 features in your data set. You only have to do is 2 raised to the power x equal to 8, and this x will actually give you the number of qubits you need. That will be 3. So 8 feature information can be represented using 3 qubits. That is given. Now, the important part you have to keep in mind while doing this exercise is you have to normalize your data before feeding into your quantum state, because it has to follow an expression of probability amplitude. That is, the modulus of square of sum of this expression should be equal to 1. This is called as amplitude embedding. Now let's quickly see what is angle embedding. Angle embedding is nothing but putting your classical information into a quantum state using phases or angles. Now, till now, what we have seen is that there is something called as probability amplitude, whose square sum has to be 1. So definitely you can use a phase form of expressing a qubit state. If you will see on the right-hand side in angle embedding, we have a mathematical expression which says that as vector psi, a cat vector psi can be expressed as cos theta with a 0 cat vector plus e raised to the power iota psi sine theta. Again, if you will square and sum this expression, you will actually get 1. Now, you can take your information, convert it into the classical information, convert it into radian form, and pass that information to this kind of expression to represent your classical information into classical quantum state. To learn or understand it better, we have added a block sphere diagram also, which represents where the theta and psi lies in the block sphere for a particular qubit. This expression in quantum circuits looks like rotations and of your qubits using x rotation and y rotation and z rotation, because these are the rotations you can see in the block sphere also. Rohit, we can move to the next slide.
Yeah, I will just want to add a few things here. So the idea of state embedding is, Ashu mentioned, that if you want to process something on a quantum computer, it has to be expressed in form of a qubit state, right? If you want to understand this further, why basis, why amplitude, and why angle embedding only, look at how a quantum state is. It is basically alpha, which is a complex number, state 0, plus beta, which is a complex number, state 1, if you look at the superposition state. Now, if you look at the 3 elements we can vary either the complex number or the state, you will get these answers. So alpha can be expressed in form of a plus iota b, where a plus iota b can be converted into an amplitude, that is under root a square plus b square, or it can be converted into a theta, cos theta minus b by a, right? So you have 3 elements from that quantum state that you can vary and encode information in. Remember, always when you want to encode the information, you need a variable. And the 3 variables that are available in a quantum state is the magnitude, the amplitude of various states, the phase difference between them, which brings angle embedding, and each of the basis states that are available. So if you have 5 qubits, you'll have 32 different states. Each of those states can encode the information. Second thing I want to add here is you have heard about superposition, entanglement, and interference. The idea is, if you look at classically, right, there are 2 types of systems which process information, deterministic and probabilistic. Quantum computation works on the probabilistic side of things in quantum domain rather than in classical domain. So you are initially given a distribution of probability over quantum states. So if there are 3 qubits, 8 quantum states with different probabilities, you manipulate those probabilities to get your answer. And that is what was expressed in this previous diagram. If you see, you start, you state embed, you get a probability distribution on these 8 states. And then slowly you manipulate these and a final probability distribution changes. And the highest probability answer is generally observed when you measure it, right? So this kind of thing happens. Over to you, Ashu.
Sure. Thanks. Yeah. Now we have understood that we require to perform certain actions to bring your classical data into a quantum state space. The next thing which is required is to design a quantum circuit. So what is a quantum circuit is built of? So it is built of certain gates. Now, what are these quantum gates? These quantum gates are similar to your logical gates in your classical system. So you're in the logical space, you have XOR gate, AND gate, NOR gate, certain kinds of gates which you use in your IC development when you are designing or inputting your classical data into a quantum space, in a classical data into a space. Just give me a sec. I think my daughter is trying to. Yeah, sorry. Yeah. So these gates are actually represented using the basic transformations and computations acting on a quantum state. So quantum gates are nothing but doing certain operations on the quantum states using certain kind of rotations, if we want to say, or certain kind of amplitude manipulations, if we want to say, making changes on their probability amplitude functions. These all things happens by representing these quantum gates in certain matrix formats too. These are very, very standard operations which have been designed by the researchers. Suppose we want to look at a Hadamard gate. So how a Hadamard gate looks like? The Hadamard gate basically looks like a 2x2 matrix where you have an expression. So the two columns can be considered as two basis vectors for that Hadamard operation. And the overall amplitude of Hadamard gate is 1 by root 2. Now, how this expression can manipulate your quantum state? Let's see a small example also. So if you will see on the left hand, bottom left side of your transformation example, it states that suppose your input quantum bit into a qubit, which we call, is in a cat notation of vector 1. That means the zeroth part of cat notation is right now having no probability amplitude to it. And you want to apply a Hadamard gate to this kind of an expression. What you will do is once you apply a Hadamard logic to this expression, you will start getting a probability distribution or of that expression into both the states, that is 0 cat as well as 1 cat. So fundamentally, what Hadamard gate is doing is it is dividing the probability amplitude to both the basis orthogonal basis vectors in it. We will see this physically happening once we'll show it in the demo part. So there is a huge list which we have shared of all the possible different quantum gates. Mostly these quantum gates are smaller in size. That means they are not more than 4x4 matrix. And mostly they apply to a single qubit, one at a time. Entanglement is a property which is expressed by controlled C0. So where you see controlled C0 circuitry, that fundamentally is expressing that you are entangling two qubits. Poly X, poly Y, poly Z, these kind of poly gates are basically used to measure the phase of a particular qubit in a certain dimension, that is X dimension, Y dimension, or Z dimension, and so on and so forth. So there are multiple gates which you can express your circuit in. Can we move to the next slide?
Yeah, just to add a small thing here.
Yeah.
So when you look at the gate model of computation again, even if you look at the classical computing domain, generally the idea is that you have a small number of basic gates and you use those to build larger circuits which can do your computation. The same idea is expressed here. Mathematically, they are represented via matrices. If you look at the physical side of things, how these gates look like in real, if I go to a real physical computer, they are currently being executed using, for example, microwave pulses. So mathematical operations done via hardware is a thing you may want to refer to if you want to have an overall understanding of how these things work. Okay. So I'll move on to the next slide. Ashu.
Yeah, thanks. Now, this is very interesting part. So till now, we have understood there are certain gates, there are certain notations. So to express, there are certain principles used for quantum computing. Now, what we will do of all of this, how we want to express the information in form of a quantum computer to represent your entire theory or entire classical data set. This is what comes into the picture, which is called as quantum circuits. So I want you all to focus on the right-hand side image, which is there. Quantum circuit is basically a combination of all these things. There is something called as initialization or a reset gate. Why is the requirement of this kind of a component in a quantum circuit? So you all need to have a fundamental starting point for everything when you bring your classical information into quantum space. Suppose you have done a state embedding using amplitude embedding, suppose. And now you want to start, because you have a lot of rows in your classical data, and you want to start training a circuit. So what you will do is you will first prepare or reset every information which is coming from a state embedded form by applying a certain kind of operations which are called as state preparation operations for your quantum circuit. This is a required operation to perform machine learning tasks in quantum computing, using quantum computing. Next part is, once you have a state preparation, there is something called as quantum gates. Now, quantum gates are basically those operations which are not controlled, which are directly used. Suppose Hadamard Gate or C0 gate, which is doing entanglement, Hadamard Gate, which is spreading the probability distribution across uniformly. So these are fundamental gates in quantum space, which we can use directly in your quantum circuit to achieve your respective goals of classification, regression, whatever objective you have. Now then comes something called as trainable quantum circuits, which we call as classically controlled quantum gates. Now, classically controlled quantum gates are essentially those potential points which can learn your data set, or you can actually control these weights, do optimization objectives, change their, make certain rotations, bring certain kind of manipulation to these gates in terms of phases, in terms of even amplitudes, if you want, if you are expressing your data that way. Doing this actually leverages or helps a person who is designing a quantum machine learning algorithm to train that quantum circuit. So this part is actually trainable, which actually will attempt to learn your information. And that manipulation is controlled using a certain kind of optimizer, which is kept outside, currently outside the quantum space, because right now we are using classical optimizers. And there is a fourth part, which is called as measurement. So suppose there is a quantum computer, you have designed your entire circuitry. How would you go ahead and understand what has happened inside it? To understand what your circuitry is behaving, how it is behaving, you need a certain kind of measurement mechanism to be placed on top of your quantum circuit to fetch that information out. So most of the time, you will see measurement gates capped at the extreme right side of any quantum circuit. They are basically used to capture the information which your circuit has learned. Now, the measurement also depends on the kind of rotations or expressions you are making to your quantum circuit. Maybe you are bringing phase changes, maybe you are bringing amplitude changes, maybe you are only focusing on two kind of rotations, rotating in X direction and Y direction. All these things will help you to identify and determine what kind of correct measurement you want to place there. Now, measurement also happens in two ways. You can directly measure or you can sample, that you will look in the coming slides. But these are the four fundamental part of any quantum circuit you want to bring in. Yeah, right, we can move to the next slide.
Yeah, so let me add a few things here. The first thing is with respect to quantum circuits and computing. If you look at the classical domain again, algorithms are generally nowadays expressed in form of, let's say, functions within libraries. So we have reached a level where we can write a behavior that we want to run on a computer. But if we go far back in classical computation, also let's say 1950s, 60s, 70s, you could have expressed your computation in form of a classical circuit. And many of you would have seen, if you go into the CPU, you'll see a unit called ALU, Arithmetic and Logic Unit. That unit is basically built out of gates. So at the end of the day, at the hardware level, we use that gate level circuitry to solve problems. As the case stands today, quantum circuits, they represent our computation. So if I give you an algorithm, the most important way to express this model of computation, the gate model, is quantum circuits. You will have to build a quantum circuit to do anything. You cannot escape this. You cannot write a Python subroutine, for example, at a high level, which can solve this. That is point number one. Second, just to give my point on the measurement side of things, since this is a probabilistic model, right? Every time you will not get the same answer. You're not going to get, if you add 2 plus 3, it will not always give you 5 in this case. Our goal is to just increase the probability of getting 5. So measurements are applied to see what the output is. So in probabilistic model, you want to enhance the probability of your answers coming out most of the time. Hence, the measurement is also part of the quantum computation we do. The third point is, if you go back to the earlier pipeline that we showed you, right? This pipeline. In this pipeline, Ashu explained state embedding, and we jumped on to the gates and circuit. That is because superposition, entanglement, interference, all three of these basically are expressed via quantum circuit. These are baked into the algorithms and expressed via quantum circuits to basically implement that algorithm. I think I will take over from here at least for 3 slides, and Ashu, then you can come back. So till now, we have been exploring the computation on gate-based. We did not talk about QML per se. We just wanted to know how gate-based computers work, and we'll move a bit fast given the time we have. Yeah. So if I go ahead, the idea is that QML on gate-based systems can be defined very simply in 2 ways: the workflow that you take and the algorithms that you have. The workflows can be designed for gate-based, annealer-based, or quantum-inspired systems. And the QML algorithms are designed for each type of quantum systems. Each of them have different type of algorithm given the way they work. They work very differently, though they want to solve problems only. Now, this is one interesting thing that you may want to look at: the evolution of gate-based QML algorithms. So it is divided into 3 domains, right? I'm looking at the right side first, then I'll go to the left side. The first domain is Qram dependent algorithms. So when you are building algorithms, the idea is, can you find good algorithms which can provide you, which can have a low time and space complexity on a particular model of computation, right? So these algorithms were found starting with HHL algorithm for linear systems of equation in 2008. And then people identified other algorithms, and they found mathematically proven speedups. For example, as Shor's algorithm say that I can get an exponential improvement on the factoring problem, these algorithms say that I can get exponential speed up in doing PCA, in doing SVM. but all of them depend on Qram. You can replace Qram and bring in real-time state embedding, but you will not get the speed up. You will be able to execute the algorithm, but you will not get the speed up that you expect from that algorithm. So it requires Qram, it requires longer circuits, not shallow circuits that we have in today's computers, and that is due to certain reasons. So these requires Qrams, fault-tolerant computers, longer circuits, and non-noisy qubits. Qubits should maintain their state. So these algorithms at this point in time cannot be applied at scale for practical problems. But once these error-corrected systems are available, once the number of qubits increase, these algorithms will become more prominent. Now, other than that, one more angle is a dequantization of these algorithms have been proposed, though we do not know for sure whether that dequantization is correct or not. What do you mean by dequantization? Somebody built a certain set of classical algorithms and said they perform as good as these Qram dependent algorithms, right? But it is still not proven, but that is one area which you can say is quantum inspired from this, which takes these algorithms and builds something which is improving classical computing. Now, this is not very practically feasible. The second domain is more practically feasible, which is a hybrid QML version. The idea is you take a parameterized quantum circuit, as Ashu was saying, and you put a classical optimization in front. So this idea is being explored by people in areas of quantum chemistry, quantum machine learning, quantum cryptography and all, to achieve what is called quantum advantage. That is building something which performs better than classical computers. And there are certain examples of it. You can see the second domain, what algorithms are there. A third generation is coming up, which is brain inspired. I will not jump into it, but you can build something which is even better than the second and can provide the quantum advantage. The left-hand side of things talk about the learning machines and types of data problem. You can have quantum data or classical data. Then you can have a classical computer or a quantum computer. So depending on these two things, you can identify different areas. So when you take classical together, you get your classical machine learning. When you take classical data and quantum machines, you get your second domain. When you take quantum, you get your first domain. And when you take quantum data and classical machines, you are basically talking about quantum systems, like, for example, data that is coming out of CERN, and putting it in classical machine learning to solve problems. Now, since second domain is more relevant, the hybrid QML, will focus on hybrid QML going forward. We do not want to look at the theoretical side, but what we are doing. So current quantum devices, as I said, have serious constraints, limited number of qubits, noisy processes that limit circuit depth. The circuit that Ashu was showing earlier, if it is very small, you cannot do much with it. Algorithms are to be expressed in form of circuits. And when did you see an algorithm which is not long enough? You do not write 2 lines of algorithm, right? You have 50 lines in classical. So that gate circuit should be big enough to process something. The hybrid algorithms are called variational quantum algorithms, which basically use a classical optimizer to train a parameterized quantum circuit, as I said earlier. It is coming out as a leading strategy to handle the currently resource-constrained quantum computers. Basically, if you want to achieve quantum advantage, this is the way to go at this point in time till you have better quantum computers available. VQA and PQC can be used to perform QML on NISQ systems. So the idea is that VQA, variational quantum algorithms, can be used in many areas, optimization, cryptography, this and that. Our focus is quantum machine learning and how that can be done on NISQ systems. NISQ systems basically are noisy intermediate scale quantum systems. That is the system today with noisy qubits and smaller circuits. Now, advantages delivered are through what we discussed earlier, compact representation of data, and hence lowering the number of parameters for optimization. We have put articles also here. You can have a look at them. Ashu, over to you.
Yeah, thanks. Now, so coming back from what we have seen till now is we know there is a circuit which has to be designed to learn the information using quantum gate-based systems. Now, this image which you see on your screen is fundamentally representing a life cycle of training a quantum gate-based circuit for a classical data. So I will just walk you through from left to right what is actually happening. So the first thing which you bring is you bring your classical data and do uh, and adopt a certain embedding strategy, which we discussed before, maybe amplitude basis or angle embedding, and perform a state preparation operation in your circuit, which is your quantum circuit. The state preparation part is fundamentally not trainable. Uh, it is just to bring all the quantum states to a certain starting point from where you can feed in your information to a quantum trainable circuit. Now, trainable circuit is something which has parameters in it. Now, parameters are actually controlled by a classical algorithm or a system which is sitting in your classical computers. It is not in your quantum computing system. You pass those parameters to a trainable quantum circuit in a quantum computer, controlling based upon their output performance, how your model is performing based upon the cost function or objective you want to achieve. Now, these trainable circuits or trainable gates, as which we call, can be rotations, can be amplitude, probability amplitudes, and in the mix of this entire trainable circuitry, there are certain operations which are required, which are pure quantum gates, which are not trainable, like C0 gate, Hadamard gate. We use these gates to achieve certain tasks or a certain objective while performing the action. Once your trainable circuitry is designed, then comes the part of your measurement. You put a measurement layer on top of it. Again, that measurement is based upon what kind of rotations you have bought, where you are moving your information, in which direction you are moving your information. Suppose you are you are turning all the rotational components in your circuitry, you are turning all the amplitude components in your circuitry. Those kind of things will determine what kind of measurements you want to do. You want to perform a sampling, you want to perform averaging on top of it. Once you have measured something, now the information rotates and comes back to a classical system. This measurement which you have gathered will be fed to a classical optimizer. Now, this classical optimizer has a responsibility to reduce the error in the actual prediction and the actual data and the predicted data. Now, this classical optimizer is actually sitting in the classical domain itself, where it is measuring that, okay, this was the actual data, this is what the system has predicted till now. Based upon that information, it will update the weights of the quantum circuit. Only those weights which are trainable will be updated again, and again this cycle will continue. This operation carries on to a certain point, which is again controllable in variational quantum circuit scenarios, where you are going to reduce or achieve a certain loss parameter which you have decided. Suppose you decide that my loss should be less than 1%. So you can, based upon that, you can run your quantum system. Now, the important part which is there is to capture the complexity of your data. How would you decide upon that? That how complex is your data? Yeah.
Sorry, just a time check. It's 12:26. So proceed in that way.
Sure. I will be a bit faster then. Yeah. So the complexity of your circuitry will complexity of your data will decide the complexity of your circuit. So if your data is too much complex, maybe you require many number of layers. So in this diagram, if you will see, what we have shown is this is a two-layered circuit with in each and every layer there is a depth of 4. Similar, so when we say quantum layer, it is similar to your neural network layer, where a certain kind of operations are performed, and you can repeat this number of layers as many a number of times based upon your complexity of your data set which is there. Yeah, Rohit, we can move to the next slide. Yeah. Now, once your system has been trained, you have designed a system which is trained, and those parameters are set for your quantum system. It has trained on a given classical data set. How to go about and generate inference, how to use those quantum systems to generate inference. Again, this kind of operation requires a quantum computer anyway. Now, what will you do now is you will upload or you will pass that quantum circuit with those trainable weight to a quantum computer. You will take your classical data, again perform the same embedding which you did in your training part. You will again do a state preparation. And this time, rather than training your weights, you will use trained weights on the quantum circuit, which is say exactly similar architecture which you used for your while you were training, and you will pass your information through this circuit. The next what will happen is once trained circuit has performed this computation and you have measured the output, you will have to interpret this measured output in your classical space, and we'll try to understand or inference it in the way you want. If it's a regression problem, then it will be a continuous number you will get. If it's a classification, you will get categorical values out of once you measure and convert it back to your classical domain. What is happening inside, Rohit, just a minute, just a small part. What is happening inside your quantum circuit is actually expressed if I take a single qubit, and there is a lot of noise in the information set. If the left hand side, if the block square, if you will see, and what your quantum circuit is actually doing is bringing that entire information, passing it through a lot of computations, and bringing it with a high probability to a certain point. So the point on the right hand side of a block sphere is the most probable point which you will get after you perform certain kind of operations. And this left hand side block sphere is actually representing your input data. So if you understand with an analogy that you pass a lot of features and then you get a classification of those, suppose you pass a particular row which has 100 features in it, and then on the right hand side the system tells you, okay, this is the probability that this particular row is belonging to this particular class. Initially, that class was all around. Suppose it was a 10 class classification problem, the information was all around. Then, because of quantum circuitry, it has isolated to a certain class with a maximum probability. That is how what happens in a quantum circuit. Next, we show what all we can do using these quantum gates. So there are a lot of operations which people or researchers have studied in terms of building hybrid architectures, including quantum circuit and neural network, latest neural network models, combining the power of both the world and designing new architectures to learn highly complex information sets. So how this particular, what all kind of things happen and how this happens, I will quickly brief it. On the left-hand side, the image shows a quantum circuit which actually is connected with a neural network with some kind of measurements in it. Initially, diagram will be in the VQC network, there was no classical neural network attached, but in this particular scenario, the researchers have designed certain algorithms where you can actually embed neural networks models on top of your quantum circuits. These neural network models are residing in your classical computer. So think it about like there is a quantum computer sitting and then there is a classical computer. Both these computers are interacting with each other and trying to understand the data together. That is the beauty of this architecture. Both the designs are helping out each other. Currently, what we have seen and observed is like these kind of architectures are performing better because of the noisy nature of the quantum systems right now. So these neural networks help reduce that random noise getting generated from quantum systems. So it stabilizes the solution. Now I will quickly jump to certain possible architectures available. Quantum circuit plus simple artificial neural nets. You can this is also represented in the image also. You can just take some neural net. Fundamentally, the optimization process which is being performed for all these networks is residing in the classical domain. Second kind of thing is you can use quantum circuits in transfer learning networks. Suppose your model has learned, you have a transfer learning model which has learned on certain domain. You can bring that model, embed with a quantum circuit and perform a certain task in that particular domain as per your requirement. GAN models with quantum circuits, you have GAN models which are trained, which are generative in nature. So you can use those generators which get trained in a GAN system. The generator model of a GAN system can actually help and act as a feature engineering component to your quantum circuit. And then you can use a quantum circuit to enhance your accuracy or precision of your model. Another type is a simple encoder network you can use, which can bring down the dimensionality from a higher dimensional classical data to a lower dimensional classical data before feeding it to a quantum system or quantum circuit. Then there can be something as quantum convolutional neural networks, where you can perform the convolutional part in the quantum space and then use a simple neural network or also a quantum circuit to train data on your images or the natural language processing problems, whichever is there in hand. And the convolutional part basically can happen in the quantum space, as we have seen how it goes. So these are certain examples which exist in this era of hybrid architectures. Cool.
Okay.
Yeah,
so
you can continue.
I will take over. So we looked at quantum machine learning and quantum machine learning on gate-based systems. As I said, there are 3 types of system we can do quantum machine learning. All will move on to annealing-based systems. So annealing-based systems have a different view to how you do machine learning or optimization. They have a different architecture from the type of systems we observe, right? So first of all, what is quantum annealing? This is a sub of, let's say, adiabatic quantum computing discipline. The idea is quantum annealing is a heuristic search algorithm for finding the global minimum of a given objective function. So this is an optimization routine per se. Now, it can be compared to something called simulated annealing, if you have heard of it. That is a classical nature-inspired optimization algorithm that is based on the process of annealing used in metallurgy and material sciences. A note about annealing is given on the right-hand side. It is a heat treatment process that alters physical and sometimes chemical properties of a material to increase its ductility and reduce its hardness. So basically, you heat something and let's say put it in water. The property of materials is going to be changed. Something very soft can become very strong suddenly, right? So just imagine taking that physical process and converting that to an algorithm. And it happens a lot. If you look at how bees collect food, or how insect swarms move, or how rivers turn, those can be converted into mathematical algorithms. Basically, nature computes, and those algorithms we are bringing in computer science. So simulated annealing in one such algorithm, with which we can draw a parallel of quantum annealing. Now, what can these quantum annealers do? There are 2 primary tasks that we are looking at. One is do optimization, so that all the optimization problems in the world can be solved, whether it is specifically optimization domain, portfolio, route, and all those things, or optimization in context of machine learning. The second thing you can do is PDF sampling, which is very useful in generative model of machine learning. So these things you can have a look at. Now, you heard about the concepts of superposition, entanglement, and interference, which are very important for the case of gate-based computers. In case of annealing-based computers, the idea is a bit different. There's something called tunneling effect that becomes very prominent. What is the tunnel effect? When you do optimization, you're looking at an energy landscape. You are seeing, okay, think yourself, you're in a big in a city, in an outside city, and you have hills and valleys, right? Now, if you want to identify the lowest point in the valley where the water resides, you will perform some sort of algorithm to reach there, right? So when you look at other algorithms like hill climbing, simulated annealing, gradient descent, these are very common terms in machine learning and optimization. You will basically try to explore this space in various manners. The image that you see here shows that if you want to identify where is the water, you'll climb on top of a hill and look at it, right? Such kind of things will basically take you time to find the minima. Quantum tunneling just passes through this hill. Just assume that you have a drill, which can cross this hill from below itself immediately without even touching anything. So quantum annealing explores this space better than what other algorithms do. Okay. So we'll move on and jump to this. So how does quantum annealer solve these optimization or sampling problems? You have to express the problem in something called a binary quadratic model, Ising model, which comes from computational physics, and I'll explain in a minute, and the QBO formulation. All three are equivalent in nature. One is mathematical, one is physics-based, one is computer science-based. Take your problem, whichever problem you want, machine learning problem, optimization problem, and code it as a QBO, right? Within the system, these quantum annealers, this problem is mapped directly onto the hardware. When it is embedded on the hardware, the quantum annealing algorithm, basically the exploration of such space via quantum annealing algorithm, will give you the required answers. So it basically, in essence, is solving the Ising model. It is looking at these are lattice type circuits. If you look at this, it is a lattice. It is showing in 2-dimensional, extended to 3-dimensional. Each of these nodes can have a value of 0 and 1. That's why the binary quadratic model. When they can have a value of 0 and 1, a certain configuration of these nodes will give you the lowest energy answer, which generally allows us to do optimization, or certain configurations of these nodes in 0 and 1 form will give you a sample out of a distribution through which you can do machine learning, for example. This is what I was talking about. The annealing systems take QBO-based, Ising-based, or BQM-based problems. And just a brief description of Ising model. This is what we looked at when somebody built, for example, the quantum annealer on the digital annealer. Those two can be looked from Ising model perspective. The mathematical expression is as direct as you see it. Each node, AJI, has a bias. So look at individual nodes, they have a bias. And neighboring nodes have a coupling strength. So these two terms can be used to express a problem. So what bias a particular node has, along with what is the connection with the neighboring node. So the problem is expressed in this way, and then the algorithm works on and identifies what configurations can be extracted, some for optimization, some for sampling for machine learning. So as I said, there are two ways we can improve. Now we were again talking about the basic concepts of annealing. I'll just move on to the QML and quantum annealers. The idea is you can improve ML tasks in two ways. Either when you look at normal machine learning, starting from data embedding, pre-processing, feature extraction, and going up to optimization, those optimizations are classical in nature, and those are slow. Neural networks take a lot of time to train. If you can identify a way to apply quantum annealing or some other form of quantum optimization to improve these routines, your training will be faster and better. So that is one way. But we will focus on the next one, which is basically learning joint probability distributions using PDF sampling. So if you look at machine learning theory, the idea is you can learn something by two ways. One, the more common is discriminative models. What is the conventional machine learning route we have been seeing? You are given a data set, you have X's, you have Y's. You just want to predict, given an X, what will be Y. That is a conditional probability model. The second says that the data that you are seeing, the data sets you have, they're coming out of some process in nature. Take that nature or academia or industry, whatever you can call it. Take that process, and can you basically build that process itself? So if we sample from that process, it says, okay, this sample is coming out for this particular process. So think about modeling all the properties of a cricketer. Now, if you identify, if you take a sample out of this, and this guy maintains all the properties of a cricketer, he's running on the field, throwing balls, or he's just walking on the road, hitting shots without any bat, those kind of things can tell you, okay, this guy could be a cricketer, right? So those kind of generative models allow you to do learning again. And that is through joint probability distribution. Now we'll talk about generative and discriminative deep learning. Deep learning goes into two ways, generative and discriminative. The two I talked about earlier. Now generative model can be done via RBM. That is the main concept. You can forget everything else, autoencoder, CNN, RN. The idea is generative models can be done via RBM, right? Now, if you look at this RBM, and if you look at the mathematical equation that is given below, it looks very similar to the Ising model that we saw earlier, right? This particular one. This particular one. Given these two are similar in nature, what you can do is you can train RBM on these systems, because you will express your problem in RBM format, your machine learning problem, and then you can submit the problem to the quantum annealer, sample from the quantum annealer, and you'll train your system. That is the idea. So this I'll give to Ashu to explain. Ashu, go a bit quicker. We have 10 minutes.
Yeah. So basically, this kind of system, how it works is like you have a classical data in hand, and generative models have a fundamental responsibility to assume a certain kind of distribution and try to fit that distribution on the data as better as optimistically as possible. So you have a prior information. The prior information is nothing but untrained density function. So in classical space, what conceptually we do is to train RBM model is use Gibbs sampling. Now Gibbs sampling is a phenomena of sampling from a given distribution set, but sequentially in nature. This is a very, very slow process. It requires a lot of time. And as the number of nodes in your RBM network increases, the time increases. But fundamentally, you will reach up to a point where your model will start predicting the distribution of your data or your input data better. In this entire process, there are three drawbacks. First drawback is it is sequential in nature, so it will consume more time. Second drawback is it gets trapped into a certain highly correlated area. So the kind of samples Gibbs sampling will generate will be highly correlated. And then again, there is a lot of burning time required, even to get through a certain region where correct distribution or correct samples are getting collected. You require to use a burning time and throw out all those initial samples because your model is trying to reach to a certain area. These are the three drawbacks which are basically mitigated by using quantum annealer-based sampling. We can move to the next slide. Yeah. In this particular thing, what we are doing is we are using quantum annealer. There are a lot of cloud partners available which help us do this action. We again do the same RBM network where we do a same prior, we take a same prior, we have a data set, we try to learn and approximate the data set using a well-known probability density function. But this time we use quantum annealers rather than Gibbs sampling. So this helps in reduce humongous amount of time while training the data. You will get a faster training, and you will also get better samples, so the accuracy will increase because this time you will get less correlated samples, better point estimation will happen, and also there is no burning time required in this scenario. It will be very, very fast. Yeah, but we can move to the next slide. Yeah. Now this is a picture which represent how a QRBM looks like and how it get trained. So a QRBM is nothing but a neural network with no interconnections between a layer, but fully connections between the layers. In a same layer, you will see no connections between the node, but in two consecutive layers, they will be fully connected. The weights which you see here are actually which are required to train to approximate your data set. So the overall idea is to reduce the entire energy of this network. The energy of this network is expressed below. If you will see, it has three components to it. The first is the self energy of the visible nodes. So in RBM, mostly there are only two nodes, which are called as visible nodes and hidden nodes. There are biases associated to each of these nodes. So the energy of this entire network can be represented as the value of the visible nodes, that is 0 or 1 multiplied with their respective biases. Same with the hidden nodes and the cross-sectional weights which are there. Now the training happens using gradient descent algorithm. But using the gradient descent, you require a probability estimation of the nodes while you are training your RBM, and there comes the picture where you require quantum annealing sampling for doing this operation. So the overall idea is to reduce the energy of the network given your data set. As much the energy of the network will reduce based upon your data set, the better the RBM networks know the real distribution of your data. That is how this entire operation works. This becomes a generative model in that scenario. And quantum tunneling is a major component which is used while doing quantum annealing sampling. So we can quickly move to the next slide.
So Ashu, we have another half an hour. We can continue up till 12:20. Okay, so
okay.
Yeah.
Okay.
Yeah.
Then in this, then I would like to add few points here also.
Sure.
Yeah. So the major complexity which is there in this particular operation is training these weights which are associated, and you would require to binarize your input data while feeding this information to your information set. So for binarizing this information, the classical data, you would require to perform one-hot encoding or certain kind of an encoding exercise, so that each and every cell holds a value either 0 or 1. This kind of information will be fed to our RVM system, and then the rest of the story will go on. Yeah, we can go on.
Thanks. So Ashu, could you please give some examples on what RPM can be used for in real life scenarios? Where have you used, and how does quantum annealers help in RPM training?
Sure. So RBMs are classically used for recommendation system. For example, a movie recommendation system, which was designed first by Netflix, it used the RBM for that. Mostly, the fundamental idea is wherever generative modeling is required, we can go ahead with RBM networks. Now, how we leveraged RBM training of RBM using quantum annealing is we used D-wave systems. These D-wave systems help us in reducing the training time. Humongous reduction in training time was observed. Again, how it happens, where this interaction with the D-wave and the RBM is used is companies like D-wave, Azure, they expose certain APIs where you can actually collect the information in terms of a JSON format of your network and submit that problem to that cloud-based annealer, where it will represent this entire network into a QBO, as Rohit expressed. QBO, or you can call out is that Ising representation of your information. This information set, once represented in Ising model, it enters your quantum annealer. Quantum annealer will take this QBO, and what it will try to perform is try to identify the lowest energy configurations. So when I say configuration, when I use the word configuration, it actually means that suppose in a network, it has 100 nodes. Each and every node can take either 0 and 1. And based upon all those values, zeros and ones, for all those different values, you will have different energy expressions, right? Suppose certain visible layer has taken 1, at another time that same visible node has taken value 0. So you have got 2 different configurations. Like that, there can be huge amount of different configurations possible. And what this annealing will do is it will try to sample from these configurations. Yeah, I think you should, okay. Let's move ahead to another concept of QML using quantum-inspired algorithms. Rohit, can we move on? Yeah. Now, till now, whatever we have observed, it was based upon utilization of quantum computers, some or the other way. If you have gate-based circuitry, you will use quantum computers to pass your gate circuitry to the system, do some measurements. If you have annealer-based systems, you will pass the Ising representation of your network or a QBO representation and perform quantum annealing on top of that and get some results out of it. What about you if you do not have any quantum computer at all, and you want to perform exercise optimistically? That entire space comes under quantum-inspired algorithms. Now, quantum-inspired algorithms are basically used to speed up the operations which you are performing, and maybe this speed up can, if it can bring better results and better accuracies uh, over the traditional approaches anyway, which we have been using for a longer time. Now, we have splitted this entire quantum-inspired approach in two fundamental domains: machine learning and quantum-inspired optimization domain. In machine learning, what happens is, or the major idea of using inspiration from quantum physics is to learn the classical data and churn the data faster. For this exercise, there are certain operations which people or the researchers have used from quantum inspiration, which perform data analysis on the data very fast, so that you can analyze the information. These operations are basically before you fit a certain kind of machine learning model on top of it. So these are called as data analytics for operations for using quantum inspiration. Another branch is where that algorithm itself was tuned on the basis of quantum physics theory. Those comes under quantum inspired machine learning algorithms. Those can be clustering algorithms, support vector machine, recommendation system, Gaussian process regression. All these methodologies are at the back end using quantum physics rather than classical physics to perform operations, but the entire operation or the computation is happening in the classical space itself. And what about the neural networks? What about the quantum circuits, which we have seen? So we have tensor networks for them. Tensor networks are basically utilizing tensors and representing those tensors. We will see a brief description about tensor networks in the coming slide. But tensor networks are basically representing classical information using tensors. And these tensors are connected in a certain network formulation. And they have a capability of expressing any quantum circuit you have in classical space. And the output or the results of the quantum circuits can be exactly mimicked here. Now, next, coming to the optimization side of it. So optimization, as Rohit initially said, the digital annealing has come into the picture after quantum annealing. It happens in your classical computer only. There are two algorithms. There are many more, but we have put two good performing optimization, parallel tampering and quantum Monte Carlo here. So parallel tampering is nothing but it is mimicking quantum annealing, but creating a lot of replicas of the given energy configuration space at certain temperatures, and then doing a mix and match on top of it. This exercise happens in digital space where multiple replicas of same cost function is being performed, but on different temperatures. Using a different temperature actually enables different starting points for your space exploration. And then again, these multiple results combined with each other, this zigzag operation explodes and exploits the configuration space much better and generate better point estimations if required in optimization process of a machine learning model. Another one is quantum Monte Carlo. Quantum Monte Carlo is actually mimicking the Monte Carlo simulation operation in quantum space. It is basically initially was used for sampling quantum physics PDF functions, but it can be used for any physical operation. It actually, because of its stochastic nature, is performing actually quantum tunneling, the same effect which you observe in pure quantum annealing operation. It starts at a very low temperature and performs this search operation where it can actually, jump from one barrier to another barrier stochastically, and it follows Schrodinger wave equation to perform Monte Carlo sampling.
Ashu, I think we can go a bit quickly so that we can jump to the demo.
Sure. Demo.
Yeah, just quickly just go through these next two slides and then.
Yeah. Now, as we told that we will have a brief look on what are tensor networks. So I will start from the top left corner, which is what is a tensor. You already know that there is a scalar which has no direction to it. It's a magnitude value. Then there is a vector which has x dimensions or n dimensions associated with it. Then there is a matrix which has which looks like a square, which has multiple vectors in it. And then comes a picture where which is something called as order 3 tensor, which looks like a cuboid if you want to visualize. All these things comes under tensor, but with different orders. So suppose scalar is the order of 0, vector is the order of 1, matrix is the order of 2. All of them can be considered as tensors. Now, what are tensor networks? Is nothing but a combination and collection of in a certain symmetry of all these tensors. This network, once designed, is called as tensor network. There are certain very standard designs, MPS design, which is a matrix product state tensor. It's a continuous chain of multiple tensors connected with each other. Then there is PEPS, then there is pre kind of tensor networks, then is MERA kind of tensor networks. Let's quickly look for certain properties of these tensor networks. So tensor networks actually are can be graphically represented as a node with certain edges associated. Number of edges tells how many or what is the order of that particular tensor. There is a classical property of tensors, that is contraction, which says that suppose you have two adjacency connected tensors, you can actually go ahead and contract and collapse these two tensors, resulting into a single tensor. And the operations won't affect each other. Even if there is a big cycle around tensor networks, you can collapse the entire thing into a single big tensor with as many number of orders as it was initially. So these are the certain kind of operations which you can observe in tensor networks theory. Tensor network theory also have something called splitting of nodes. Splitting of nodes is nothing. You have a big tensor, you can split that into multiple of small tensors. Splitting actually enables in reduction of your number of trainable parameters. Suppose I will just quickly give a brief example. Suppose there is a transformer with which has 1 lakh parameter or 1 million parameters. You can use tensor network properties to reduce 1 million trainable parameters to suppose 0.1 million trainable parameters. That is the strength, and you will not lose much on the performance accuracies. That is the power of tensor networks. How or where is the qubit here? How you are going to position the qubits? So qubit is nothing but the dangling edge of a tensor network. Suppose you have a tensor, the dangling edges which are there on the qubit are which are on the edge are actually the qubits. Now, so if I give a quick example of a 2 qubit state, it can be represented as a 2D tensor, which would denote by a matrix of 2 indices, and the representation is of that psi in terms of a tensor. Matrix is represented below, which has 4 orthogonal bases: psi 0, 0, psi 0, 1, psi 1, 0, and psi 1, 1. This is how you actually can go ahead and express the tensors. Yeah.
I think we can move on. We are losing time. So so this is one of the examples of a quantum-inspired algorithm. You can read about quantum Monte Carlo, parallel tempering and all. The basic idea is you can use certain classical systems to improve optimization of machine learning routines without having a quantum computer. Something has been developed as a classical system too, which mimics the quantum computers. This is the base. So if you look at gate-based systems, you can reach out to IBM Qiskit, Google, Circ, Rigetti, INQ, all these companies. You can use their quantum computers. If you want to do annealing-based, you can reach out to D-Wave, for example. But if you want to do QIO, where do you go? So quantum-inspired optimization or quantum machine learning. So there are open source algorithms that are available, papers that are available that you'll have to convert to algorithms. Or you can go to Azure QIO, which basically allows you to do sampling and optimization using digital annealers and the algorithms that you just saw, Monte Carlo and all. You have to create an Azure account and all, but Azure QIO provides you an opportunity to utilize these algorithms. So if you look at the overall flow that is here, the end where we were looking at the quantum annealers, Azure QIO sits now. So you can replace that quantum annealer by Azure QIO, and it will do a similar job of what the annealer was doing in terms of sampling or estimation. So now I'll move on to Qiskit, the gateway system. Okay. So when we look at QML on cloud, we will talk about this, how do you access QML on cloud? So this is the end user. We generally use web. You pass the training data to a partner cloud. This partner cloud is Qiskit, Circ, AWS, Azure, Google. That training data is passed to a training VM. That training VM contacts the quantum computers. This quantum computer, it is not like our general computers, which are sitting in cubicles with us. They are kept in separate facilities at very low temperatures in most of the cases, and there the computation is being done. So this particularly, these results go via this pipeline, and similarly the inference data is moved, right? Now, some names that I was mentioning, I have mentioned below also, quantum cloud vendors or general vendors that are available. Now, this is Qiskit development roadmap, something which basically says in which year what will be available. So idea is to find a big computer which works, which is fault tolerant and correct errors. That is sometime below. Google has said 2029. INQ has said 5 years from now. These kind of things have been mentioned so that we can achieve the advantage that we want. Similarly, IBM has given a roadmap. So they have Falcon, Hummingbird, Eagle, Osprey, Condor. All these are chips that they have built, and these chips will take them through till 2026, somewhere in the range of 1 million plus qubits they want to achieve. So once that is available, you can solve very big problems also. This is their Qiskit Aqua framework, which talks about all the types of libraries we talked about. You saw earlier open assembly language level, circuit level, and all other levels. But on top of it, when you do any classical algorithm today, you look at the level of libraries from perspective of AI. So scikit-learn on Python is a AI-related or math-related library. For chemistry, you have some certain other classical library. The quantum vendors are also going in that direction. They are creating domain-specific libraries. So Qiskit Aqua is one such library. Google will have something. Penny Lane by Xanadu has something. Google Circ has something. But here, chemistry, AI, optimization, and finance, there are different libraries. I would request you to explore this separately so that you can develop applications on your own. And this particular library is built for the current quantum computers, which are not that, which have noise and not fault tolerant. So Ashu, quickly, please, rather what I'll do is Ashu just go through the QML knowledge resources and you can give the demo and close it, okay?
Yeah, sure.
Yeah, so this is the knowledge resources that we have. There are certain courses I have mentioned here. So Quantum ML by University of Toronto on edX, Quantum Computing for Beginners on Udemy, Professional Certificate in Quantum Tech by Delft. All these will help you. Some of these are paid, some of these are free, but many of those will help you understand Quantum ML better. It is not a very, very simple field. You need the exact right resources, which we have done after looking at thousands of them. So these are the channels and resources we looked at to improve our understanding. You can look at YouTube channels and links. The first one is very, very interesting. The map of quantum computing. It ties everything together that we have been talking about. All type of computers, all type of algorithms, who's developing what. The map is given. So this you can look at. Then you can look at the Qiskit channel, of course. You can look at specifically how quantum annealing works. Very nice 4-part video that you can have. Then there's a quantum ML channel, which explains in detail the mathematical basis of quantum machine learning. You can look at these 3 books. One is Qiskit free book that you can download from the link. You can look at other 2 books. These are very interesting books. There are not many books, many good books on quantum computation and information theory. These 2 books looked very good to us. They explain things these things more easily than not. Yeah, you can look at GitHub links, D-Wave, IBM Qiskit Terra, Google Circ, Penny Lane. This awesome quantum software contains all the details that you need from quantum GitHub standpoint, what all channels are available to you. Similarly, these are some miscellaneous links, some very good links that will be helpful to you. So I'm not going through this. What I'll do is I'll hand it over to Ashu. Ashu, if you can quickly go through the platform, I think we need to answer certain questions. Do you want to answer the question and then go to the platform, Ashu?
We can do that.
Sure. So
let's finish this demo and then we can have a Q&A
okay.
session.
So I'll hand it over to you. Do you want to share your screen?
I will share. Yeah,
I'll stop sharing.
Yeah. Okay. Okay, please let me know if my screen is visible.
Yes, sir, your screen is visible.
Okay. Okay. There is a quick link which we have kept for people to go to this demo part. We can share this document also for first starters who want to start exploring IBM Qiskit platform. Let's start. So this is the fundamental first screen, guys, which represents how the IBM Qiskit platforms looks like. Once, so to reach to this point, you will have to perform sign up with IBM quantum computing IBM.com, and you will have to give an email address to it. And once they validate your email address, you will be here. Today we are just going to present two important parts of this. One is Composer, which will give you an overview how quantum computing works. You can design your circuit graphically. Another one is a Jupyter notebook kind of a style where you can perform programming. So let's quickly begin to the Composer part. I am launching the Composer. Cool. So this is something which I was trying before, but I will do it a new file for you. This entire screen is a representation of IBM's quantum computing platform. There are a lot of features to it. We will showcase certain features quickly. So this kind, if you can see my mouse hovering, this is a place where you can get different qubits available to you. This is a simulation design where you can actually practice add and remove qubits, which if you want. So let me put a basic operation on top of a particular qubit. I have placed the Hadamard Gate on this particular bit. As you know, the Hadamard Gate is nothing but a probability distribution distributor. So the output, if you will see, is if I will quickly remove, if I will delete this also, and then, yeah. If I suppose I used only one single qubit, and I applied a Hadamard Gate on top of it, what is the output? It has divided the information into 0 and 1 with equal probability. It's an expected output, we already know. Let's add another qubit to it, put another Hadamard Gate on top of it. Now what will happen? Now what you see, you have, so eventually you will end up into 4 different states, 0, 0, 0, 1, 1, 0, 1, 1. If you apply Hadamard on all of them, the probability distribution is equal. Let's apply measurement on top of, so let's apply C0 gate. Let's see what happens with the C0 gate. So, we have applied a C0 gate on top of that, and let's apply a poly Z measurement on top of that. Let's see what happens using this. Hey, what happened? Wow. So this is actually, so you see there is a slight shift in the probability distribution. Let's apply another measurement and see what happens on bit 2. Oh, wow. And you see the probability again has reduced of this the design with an equal probability in all of the states. So this is how you can quickly design your different quantum circuits. Now, once you have designed your quantum circuit, on the right-hand side, you can see a code automatically being written in. So there are OpenQSM. There is another a library of writing the codes. Again, if you will write, if somebody knows this language and write a program in it, it will be automatically reflected here in your quantum circuit. Now, suppose if you want to run your machine, run your circuit, you can click on setup and run. There are a lot of machines available here. You can select any of them. The major criteria is if you can see if you can select that machine which has least number of pending jobs, then you can select that one. Suppose I go with let's say only this one. If we go, so here you can mention the number of operations which we call in which IBM calls out as shorts. It will give that many number of attempts to the circuit. As we already mentioned, measurements are probabilistic. They will not give you exact results every time. So you can select that. Suppose you want to see more details about this particular machine, you can click on see details. Now this represents a lot of information about this particular machine. I will go quickly to few of them. QV is a very important factor, which is called as quantum volume. Quantum volume represents the capability of that particular machine to represent a circuit and do computations on top of it. So it's a straight away measurement of this power of a particular machine. If this power increases, that means if QV is increasing, you can directly call out it's a better machine in terms of power and turning the data with bigger quantum circuits. Then I will quickly tell about what is readout average. It is the error rate which a measurement while measuring the quantum circuit, the quantum system is doing. So this expression is suppose in every 1,000 iteration, 48 operations will have errors in it. Then let's see. There is an expression called as CLOP, which is nothing but.
Ashu, I think you can jump onto the machine learning module and just quickly show how you can do it via Jupyter on this.
Sure.
And then we can jump to questions. We have 5 minutes left.
Okay, fine. Then we can run this code. So if you press that button, it will start running. I will just show you there is something called as composer jobs, where you can click and see what all jobs you have submitted, if they are completed or not. That kind of information you will see in this section. So this is how you can leverage a lot of efficiencies in your system. Let's quickly jump to the lab part of it, where Jupyter notebooks are residing. And we will just give a small demo of quantum machine learning operation happening using Qiskit. So it is opening right now.
So Ashu, you can just show, maybe executing will take time. The idea is
I will
how
just
to
show,
just show.
Yeah.
We'll go through the questionnaire then quickly.
Sure. Okay. So for the demonstration's sake, we have kept a regression model classifier using neural networks. This neural networks is basically using quantum gate circuitry at the backend. There are a lot of frameworks available. We will in Qiskit to represent your information or your network. There's something called as neural network classifier. This neural network classifier is a mechanism in which you can design and define your NZ. NZ is something which is named to a quantum circuit in terms of raw language. But we will quickly show what all are the backends. So if you suppose you want to see what all backends are there, AER, as Rohit stated, has provided these many backends. These are all simulators, not actual systems. But IBM Q is another backend framework which provides some simulators as well as quantum machines. These all names so you would have also seen when we were seeing the composer part. Same names are coming up here too. Let's jump to a classification problem. So this section is nothing but defining a particular data set with X and Y. The data set looks like this. These are the X's, these are the Y's. It's very, very simple data which we have prepared. The data set looks like this. We want to identify the or develop a classification algorithm on top of it using variational quantum circuits. So VQC is using a quantum circuit quantum neural network, another library beneath it, and has written a wrapper on top of it. Circuit QNN is nothing but a quantum neural network circuit which is used to develop your quantum circuit. Now, callback function is nothing but a collector function. Once an operation of optimization is performed, it just collects the output which is coming out from it. So we are not doing it for append function. We are appending the optimization operations to have a visualization at the end. Now, what is a feature map? So feature map, as we showed, the state embedding part. This is the state embedding which we are doing. Now we are putting a real amplitude NZ on top of the state, the embedding which we have done. This is the section which is representing the variational quantum circuit. So we are actually passing our feature map to it, our NZ to it, what kind of optimizer we want to use on top of it, and the instance on which this entire thing will run, and a callback function which will, this will be the output of once the VQC is performed. This is a graphical representation of your feature map. There are a lot of rotational and quantum gate operations performed on the qubits. Why 2 qubits? Because we were having only 2 features initially in our data set, if you see. So we are using phase embedding or angle embedding in mix with quantum gate circuitry to design our state embedding process. This is a simple NZ circuit which is trainable in nature. It is kept after your state preparation. Then once this exercise is done, we just fit our model. Fitting our model requires one hot encoding in this kind of a framework. And this is the result, how it looks like. Once you apply this operation, the model start fitting on the data which we have provided. The accuracy right now is very, it's like 0.5. So not great, but just for a representative perspective, it is okay. This is again a pictorial representation which all classes we have.
I think we can stop it for now. We can go to the questions. So the idea is, guys, you can use IBM Quantum Lab. You can use the composer to design general circuits, and you can look at the cases of different quantum machine learning algorithms to do classification and regression. The code will look very similar to what you are doing in your scikit-learn and all libraries using .fit and all. Only thing that you have to understand is there are quantum circuits that you have to design. There are certain ansatz, basically approximate circuits that have been given to you. You can reuse them. You can then train them. That is the idea that you have to go with. Ashu, you can open the questions once. Or let me read it. So quickly just going to the questions. So the first one is how to separate.
Share the screen also.
Okay, let me share. It will take 2 more minutes, team. That's it. Let me know if you can see my screen. Okay. Yeah. Ashu, I hope you can see the screen.
I can see.
Yeah. So the first question is from Ramesh: how to separate initializing qubits from running algorithm several times? I'm not sure what does that mean. Initializing qubits and running the training algorithms are 2 different things.
Yes.
Your workflows, within your workflow, you initialize the qubits once, and then the algorithm is run once for you. When multiple times this training algorithm is running, that may mean you have set epochs and all to basically train that algorithm.
So you require multiple times to do this operation, but it happens in a quantum computer itself. So yeah, it's quite fast.
Next is from Rajesh: how to estimate the complexity of variational quantum circuit. If a quantum circuit of n qubits that uses alternating operators to build the network. So what is the complexity of this circuit? There is nothing called complexity of a circuit per se. At this point in time, we are looking at shallow circuits where only a small number of gates can be used to implement any algorithm. You can define in terms of number of gates, let's say, or number of layers if you want to use. So a variational quantum circuit of 5 layers with 4 gates each. You can talk also in terms of what elements you are introducing: superposition, entanglement, and interference. If you're introducing all 3 angles, so Hadamard plus C0 is entanglement. Only Hadamard is your superposition. The rotational gates and all introduce interference. These kind of things, when you look at, you can define the complexity of the circuit, what elements you have introduced, basically. Next
just to add to it, if you really are expecting to calculate the complexity, these are all tensor multiplication problems, and that happens in quantum space quite fast. So you can measure it using mathematical expressions of matrix multiplication.
Sure. Next is Pradeep. What is the advantage of quantum machine learning over traditional machine learning? I think we covered that in our slide. Please go through that to understand it. Idea is faster and better machine learning in comparison to classical at a high level. I think that is no, there's more. Okay. Nivedita, is any probable applicability of an AI or machine learning? We gave multiple examples. Look at the deck once we share it. Quantum computers can handle large data, big data. That is one of the ideas, as we said. Compact information representation once available. You can put big data in a smaller format and then you can use it to do whatever you want. The limitations, Ashu has mentioned that it is the noisy nature of quantum particle, cost-expensive quantum computers, and Qram unavailability at this point in time. Going forward, there are advantages, not disadvantages. Ravi, how is quantum machine learning reversible? It uses reversible model of computation. All the gates are reversible in
Reversible,
nature.
yeah.
If given an input, you get an output. Then if the same output is given, you can identify the input. That's why it is called reversible model of computation. And that happens also in classical. If you change the gates from NOT or to Toffoli gate, the model again becomes reversible. So in quantum case, it is quantum gates. That's all. So these were last of the questions. This is all from our side. Please let us know if you can close the webinar.
Sir,
thank you everyone for joining.
Sir, thanks a lot for joining. On behalf of Photonics Valley Corporation, on behalf of Government of Telangana, we would like to thank the Emphasis team, Rohit Patel Garu and your team. You really started off with very basics. What is quantum computing? From there, you started off from very basics, and there you went up deep into your topic and including in the practical application of the topic. I'm sure, in fact, a person like me who is not technically sound, who is just an MBA graduate, but still I could understand most of it, what you've been trying to explain. Really appreciate your efforts. Really appreciate your efforts. And one kind request to each one of your team, sir. Sir, day after tomorrow, that is on 15th. On 15th of April, between 12 to 1, we have got industry orientation session. Wherein all the industry heads from all the industries. In fact, Jay Ganesh Garu, yesterday evening, we had a word with Jay Ganesh Garu, and Jay Ganesh Garu has already confirmed that he will also be joining the session on between 12 to 1. Sure. So we request each one of you and your team members to please join the session between 12 to 1. It will start at 12 o'clock. It will end at 1 o'clock. It will be industry perspective. When I say industry perspective, it will be mainly 2 points. One, what industry is expecting from the students in terms of quantum computing, and industry opportunities. What industry opportunities are available for the students in terms of placements tomorrow morning? Sure, 100%. Right. So my kind invitation to each one of you to request, take this as an invitation and request you all to join during the session from 12 to 1 day after tomorrow morning. 100%. Dr. Jay will inform us for sure if he has already agreed to you. We'll get to know that. Thank you. It is my personal invitation to each one of you. 100%. Yes. I'll ask rest of the team members also to join. It will be helpful for us also. To just inform you, our viewership across various social media handles and including the TSAT TV, it's actually running in lakhs today. Yeah. I really appreciate the initiative you have taken in educating students on high tech that is coming up. It's a very good initiative that I see, because India needs to move forward in that direction. Yes, sir. And Government of Telangana is also coming up 2 months down the line. We're also coming up with placement-based intensive training program in quantum computing. And again, we're going to align with all of you again. Nice. Good. Thanks a lot once again. Thank you. Have a good day. Have a good day, everyone. Thanks for joining. Thank you, sir.
Thanks for joining. Thanks, sir.
తెలంగాణ యువతకు టీశాట్ మరో అద్భుత అవకాశాన్ని అందిస్తుంది. ప్రభుత్వం నిర్వహించే